If you followed the financial markets at all in 2025, you probably watched a metal we barely think about have a year so dramatic it should have its own movie franchise.
Oh, absolutely.
Forget gold, forget Bitcoin. We are talking about silver.
Silver, the metal you might associate with, old coins or maybe a nice pair of earrings, it permanently shed that sleepy reputation by the end of 2025.
Yeah.
It became the most exciting and, frankly, terrifying story in the industrial supply chain.
Terrifying is exactly the right word. We watched the price, which started the year around, what, $28, just undergo this massive, almost unprecedented rally.
It soared by 181%.
181%, hitting an all-time record of $83.62 per ounce on December 28th. I mean, it was a financial event that signaled a profound structural change in the global economy.
And what this price surge means, fundamentally, is that silver has officially transitioned. It's moved from being, well, primarily a monetary hedge, something people bought to store wealth, to being an absolutely critical industrial commodity.
Oh, the rally wasn't just speculation.
Not at all. I mean, speculation was there, but it was anchored in genuine physical scarcity driven by technological need.
And that is the core mission of this deep dive.
Yeah.
To explain why this quiet metal suddenly became the irreplaceable component, the vibranium of modern industry, hiding in plain sight until the system realized just how fundamentally necessary it is.
And the numbers proving this necessity they're stark. Silver is facing a structural supply deficit.
Meaning demand consistently outstrips supply.
Consistently, year after year. The projection for 2025 was a shortfall of somewhere between 115 to 120 million ounces.
And that was the fifth consecutive year of undersupply.
Fifth year straight, which tells you, this isn't a shipping problem or some momentary blip. It's a systemic gap.
And industrial applications are the main driver.
They're the primary driver now, yeah, consuming over half of the estimated 1.3 billion ounces used annually.
So where's the supply problem coming from? Why can't we just mine more?
Well, that's the root of it. Only about 28% of global silver supply comes from primary silver mines. Most of it is a byproduct of mining for other things.
Like copper and zinc.
Exactly, copper, lead, and zinc. So if the price of silver skyrockets, those companies can't just, immediately ramp up production because silver isn't their main focus.
Okay, so we have this rapidly increasing inelastic industrial demand running headfirst into a supply chain that just can't pivot quickly.
That's the crisis in a nutshell.
All right, let's unpack that demand side.
Yeah.
Why is silver so irreplaceable in our tech?
It all comes down to one fundamental physical property. Silver has unparalleled electrical conductivity. It is the world's most electrically conductive element.
Better than copper. Better than gold.
Superior to every other element we can use in engineering, which is why substitution is such a nightmare.
Let's start with electronics then. The single largest industrial consumer, using roughly 35% of total global demand in 2023. Where's it specifically needed inside our devices?
Think about the incredibly complex wiring inside microprocessors. Silver is the interconnecting material on silicon wafers. It's essential for high-frequency applications.
So as we move to smaller and smaller chips.
Right. As semiconductor architecture advances toward the incredibly small 3-nanometer nodes, that minimal electrical resistance becomes non-negotiable.
If you use something else, you get more heat.
More heat, and you slow down data transfer. It's a performance killer. So as our computers get smaller and faster, silver becomes more critical, not less.
And it's not just the main processor. I was fascinated by these tiny components called multi-layer ceramic capacitors, or MLCCs.
Oh, they are tiny but mighty. A standard 4G smartphone has about 730 of them.
But a 5G device has way more.
Way more. It exceeds 1,000 per unit. And these little things regulate current and voltage, and an estimated 70% of them use silver-based electrodes.
So the global shift to 5G, EVs, AI chips, all of that created this immediate incremental demand that tightened the entire market. Okay, if we shift gears to the global green transition, solar photovoltaic tech is the next major drain.
Huge. Solar consumes about 10% of global supply now, and it's projected to hit 15 to 20% by 2030.
So where does the silver go in a solar panel?
The silver paste is what's critical. It creates the little fingers on the cell that collect the electrons generated when sunlight hits the silicon.
And manufacturers have been trying to use less of it, right? This thrifting idea.
Oh, they've tried hard. We've seen consumption drop from 521 milligrams per cell back in 2009 down to about 111 milligrams today. On the surface, that sounds like a major efficiency win.
But There's a paradox here that I found so surprising. The technology itself is fighting against those efficiency gains.
Precisely. We're all moving toward these advanced high-efficiency cells like TOPCon or tunnel oxide passivated contact.
And they're better at converting sunlight.
Far better. But they actually require up to 50% more silver per cell than the older conventional designs.
Wow. So humanity's drive for better green energy efficiency is actually accelerating the depletion of the one critical resource needed to build it.
That's the fundamental dilemma.
We've covered electronics and solar, but what amazed me was how many other critical applications exist, starting with silver's centuries-old reputation as an antimicrobial powerhouse.
And what's fascinating here is how modern science has optimized that. We now understand that silver ions use a multimodal attack on pathogens. Think of it as a triple threat strategy.
A triple threat? How does that work?
Okay, so first, they disrupt the bacterial cell membrane, which causes it to leak. Second, they get inside the cell and inhibit cellular respiration. They basically suffocate it.
And the third?
And third, they bind to critical enzyme active sites inside the cell, essentially gumming up all the internal machinery.
That multi-pronged assault sounds incredibly difficult for bacteria to evolve resistance to.
It is. This significantly reduces the likelihood of antibiotic resistance developing, which makes silver vital in the fight against superbugs like MRSA.
And that's why we see it in advanced wound dressings and coatings on medical implants.
Exactly, for things like diabetic foot ulcers and to prevent hospital-acquired infections.
So moving from the hospital to the high-tech lab, we get into nanotechnology and sensing. This is where silver gives industry a kind of a spider sense using silver nanoparticles.
Right, or AGNPs. When you shrink silver down to between 1 and 100 nanometers, it exhibits all these unique properties because of its massive surface area. Specifically, we look at something called localized surface plasmon resonance.
Okay, hold on. Plasmon resonance. What is that in simple terms? Why should we care?
Fair enough. Think of it like a tiny bell ringing. LSPR is the collective oscillation of free electrons when light hits the surface of that nanoparticle.
So the light makes the electrons vibrate together.
And when that bell rings, it generates a super strong localized optical field. Scientists exploit this in a technique called surface-enhanced Raman scattering, or SERS.
And what does SERS actually do for us? What's the practical application of this incredibly complicated-sounding physics?
It allows for detection of chemicals at unbelievably low femtomolar concentrations.
Femtomolar, that sounds small.
It's 10 to the power of minus 15 molar. To put that in perspective, that's like being able to detect one specific molecule of a contaminant in an Olympic-sized swimming pool.
Incredible. And that's used for biochemical sensing, environmental monitoring.
And even detecting explosives.
Wow. Okay, one last industrial use before we hit the price crisis. Catalysis. Silver is a hidden giant in chemical manufacturing.
A huge one. It catalyzes 2 of the world's largest industrial syntheses, consuming 110 million ounces a year.
We're talking about ethylene oxide.
For polyester and antifreeze, yep. And formaldehyde, which is used for resins and adhesives in, well, everything.
I saw some fascinating research here about making this process cleaner. Something about nickel atoms.
Yes. Researchers found that incorporating individual nickel atoms into silver catalysts dramatically improves efficiency in ethylene oxide production.
Which is a big deal.
It's a huge materials science victory. It boosts yield, but crucially, it also reduces CO2 emissions and eliminates the need for toxic chlorine, which was essential before.
So even while consumption is high, innovation is working hard to mitigate the environmental footprint.
Trying to, yes.
Now let's turn back to those headlines. We've established the fundamental irreplaceable demand. But what exactly caused silver's price to explode by 181% to over $83 in 2025?
It was a perfect storm, and it started with global finance.
The macroeconomics.
Right. Late in 2025, the Federal Reserve started signaling rate cuts that reduced real yields on bonds, making a non-yielding asset like silver much more attractive.
And the dollar was weakening at the same time.
Which made it cheaper for international buyers to acquire the metal. But the real urgency, the real catalyst, was regulation and geopolitics.
This is when silver got its new strategic status.
That's it. In August 2025, the U.S. Department of Interior officially designated silver as a critical mineral.
Putting it in the same league as lithium and cobalt.
Exactly. And that designation fundamentally shifted how governments and corporations treated it. It triggered strategic stockpiling. Silver was now vital to national security.
And then China made an announcement.
Right. China announced new export licensing requirements for silver starting in January 2026. That created a massive rush by Western buyers to secure supplies before any potential restrictions kicked in.
Couple that with the inelastic demand we talked about.
Inelastic is the word. Sectors like solar, AI, and especially electric vehicles cannot easily cut back. An EV uses 67 to 79% more silver than a gas-powered car.
And if they try to substitute it?
The result is unacceptable performance degradation. The sources are very clear on that.
So just like vibranium, you can't swap it out for something cheaper without losing the fundamental performance that makes the technology valuable. The price rally was locked in.
It was, until the massive correction. We hit the peak of $83.62 on December 28th, only to see the market reverse sharply the very next day.
It collapsed to $73.72 per ounce. And this wasn't a natural market cooling. This was a clear intervention.
It was a classic exchange intervention. This is where the mechanics of high-stakes finance really matter. The CME Group, which handles silver futures, stepped in.
They raised the initial margin requirements
By 13.6%, and that was their second hike in just 2 weeks.
So for our audience, margin is the minimum deposit you need to hold a leveraged trade.
Right, so when the CME raises the margin, they are demanding that traders put up significantly more cash immediately just to keep their existing positions open.
They effectively forced a massive fire sale.
That's what it was. They demanded more money than many leveraged speculators had, forcing them to liquidate their positions whether they wanted to sell or not. It was a direct circuit breaker.
And this was compared to the Silver Thursday events of 2011.
Explicitly. Speculative leverage had built up to unsustainable levels, and the CME intervention caused an 11% drop in value within hours. It was a reminder that while scarcity is real, the financial market is highly fragile.
So what does this sustained high price mean for the industries that rely on this metal? Even at $70 an ounce, the cost pressures must be acute.
Oh, they are. Silver now comprises about 15% of solar module manufacturing costs.
So manufacturers are racing to adapt with those thrifting strategies.
Absolutely. They are moving to zero busbar or zero BB solar technology and ultra-fine line printing to try and reduce silver loading by maybe 10 to 20%.
But those strategies and the hope of substituting with copper, that all takes time, right?
A lot of time. Copper substitution, while it sounds promising, requires complex manufacturing changes and, 6 to 18 months of rigorous testing and validation.
Because these things need to last for decades out in the field.
Exactly. So that cost burden on the green transition is going to persist well into 2026 and 2027 while the industry adapts.
Okay, let's summarize the key takeaways from this deep dive into the world's most critical precious metal.
First, I think, is that silver has permanently transitioned. It is now an indispensable high-tech industrial commodity, critical to the next generation of electronics, solar, EVs. Its role is non-negotiable.
Second, that explosive 2025 rally was driven by a convergence of things. Inelastic industrial demand, severe structural supply constraints,
Because it's mostly a mining byproduct.
and its new geopolitical status as a critical mineral.
And third, while the physical scarcity is absolutely real, the market itself is volatile. Speculative leverage makes the price vulnerable to these sudden, sharp corrections triggered by exchange interventions.
Finally, we have to look ahead at sustainability. Given these deficits, the recycling rate for silver is critically low. It's hovering around 15 to 20% of total supply.
Which is just not sustainable. It means we have to focus on innovative recovery methods. Research into things like laser ablation to recover nanoparticles from old solar panels.
Or even using bacteria.
Yeah, advanced bioleaching. Using specialized bacteria like Thiobacillus ferroxidans to metabolize and recover silver from e-waste. These advanced methods are really the only path to mitigating future supply crises.
Which leaves us with the final provocative question for you to mull over. Given silver's central irreplaceable role in all clean energy and high-performance electronics, if persistent structural deficits keep the price above $70 per ounce, will silver's scarcity inadvertently become the highest cost bottleneck, slowing the global transition to net zero technology?